Hello students, in this video I'll discuss some problems on Laurent's theorem. It's the part of complex analysis, mathematics paper 3, BSc 6th semester, Karnataka University, Dharwad. Now I discuss the examples on Laurent's theorem. Before I would like to see those problems, we'll see the statements of Laurent's theorem. Suppose a function f of z is analytic in a closed ring bounded by two concentric circles C and C1 with the center at A and radii, that is R and R1. Then this R is greater as compared to this radius of the circle C1. If you take any point of z inside the annular region between the C and C1 circles, then expansion of f of z equal to summation of an into z minus a power n. So where n is running from 0 to infinity, where these an is the integral function that you can have, that is the integration 1 over 2 pi I into integration of f of t dt over t minus a power n plus 1. And then plus summation of bn into z minus a power minus n. It means what? Bn by z minus a power n, where n is running from 1 to infinity. It is the contribution given by, that is the Laurent's, and this is the contribution has contributed by Taylor. So that it is what we have. This bn expression is, it is also integration that 1 over 2 pi I into integration of f of t dt over t minus a power minus n plus 1. Now I need to discuss that examples on that Laurent's theorem. Now we can see that first problem, f of z equal to 1 over z minus 2 into z minus 3 whole square in power of z. It's valid for 2 less than mod z less than 3 then. Just we can see that this domain is 2 less than mod z and mod less than 3. It means mod z is greater than 2 and mod z is less than 3. This is the domain of this circle is less than 2 and 3 then. So that is what? It lies between 2 and 3. Now I need to see that here 2 is less than mod z and mod z is less than 3. It means 2 by mod z is, I want to make it as less than 1. So that's what I am taking, it is 2 by mod z less than 1. And mod z divided by 3 less than 1, it is what that. Now I take this is a function. Let us take that function, given function. And you split up these terms by partial fractions. And once we have got it, those partial fractions and split it, the form is this form. And then we can take it here because here we can take it, that is the we have taken, that is the 3 is outside because mod z is less than 3 then. That's what I am z by 3 I am taking, plus 2 by this again here also we can take it 3 outside in the first in the second expression, and here also you can take it see that here z I am taking outside because since mod z is greater than 2 then. That's what I am taking, it is the z outside you can take it. Then once we have taken all the constants and variables outside and take to the numerator and expand this using the binomial expansion. So this expansion of this 1 minus 2 by z power minus 1 expansion is this one. This 1 plus x square etc. form, that is what there. And this also, that is the form looks like the same, that is the one. If you take a minus out, it's minus becomes a plus there. And then it becomes 1 minus z by 3, it is 1 minus x form to the power of minus 1 form. So that the expansion is 1 plus z by 3 plus z square by 3 square, that is 9, plus so on that. And you can take 2 by 9 here again. If you take, that is the here also you can take it outside of minus actually here. So then it would have, that is the form is here. So then actually this is the expression for that. So then what it would be that 1 plus 2z by 2z by that is the 3 and 3z square by this one 9. So that is what, because 2 by 9, so that expansion is there. Here the first series is valid for this is the 2 by mod z less than 1, as we have seen that. It means what, mod z is greater than 2. It is that. And the second and third series is valid for mod z by 3 less than 1. And here also mod z by 3 less than 1. It means what, mod z less than 3 there. It means both all the series, these terms of all the series, this is within the mod z less than 3 there. So that for mod z less than 3, all the series are valid there. That is the reasons of radius of convergence of that series there. So then we can take it another problem here, which is in non-negative powers of z, and discuss its validity also. Now here also we have a 2 and 3 there. Again we can take it, that is the 2 mod z less than mod z less than 3 and 2 less than this, as good as we have done it previously. And you can split up the terms by partial fractions using that. And then we have here minus 1 by 2, that here that if you take that is the 2 outside, then it becomes that 1 plus z by 2. And here if you take that is because since it is the less than 1, because 2 and 3 it is less than 3, that I wanted to see that. And then we have a expansion form of these two. Both are in, that is the it is the form, that is the minus 1 by 2 into 1 minus z by 2 plus z square by 4, and the second term of that, the expansion of that one is again, that is the, both are, it is the contribution, it is the in the Taylor series form there. So here first series is valid for mod z less than 2 and second series is valid for mod z less than 3. So that it is valid within, that is the mod that. That's why, because since it is mod z less than 2 there, so that is less than 3 also there. That is there. So that's what. Therefore, for mod z less than 2, both the series are valid there. Further, you can simplify it further by taking the like terms of z power there, and simplified form of this f of z is this there. And now we can see in the third problem there, and here also, that is 1 by z plus 1 into z plus 3 in a series valid for mod z less than 1. So keep remember here also, since mod z is less than 1, it is also less than 3 also there. So that it is obviously that. In that case, you can, in the first case, it is the first term, you can take mod z is less than 1 as well as mod z by 3 is less than 1. So you can expand, split up in these terms of this function in by partial fractions, and then we have got it that form. And then what we do here, again those are also, that is all the terms, it should be in the form of Taylor series form, because since all the terms of z in the numerator, that's what I am telling it as it is. Those two series form are Taylor series form. First series it is valid for mod z less than 1, and second series mod z less than 3 then. So for mod z, hence for mod z less than 3, both series are valid here. And further you can simplify that, so that a simplification answer is by grouping the terms of z power 0, z power 1, z power 2, etc. that the terms are there, which is also valid for, that is the mod z less than 1. So then you go for the next problem there, that is expand the function, that is z plus 1 by z minus 1 into z plus 3 in a series valid for 3 discussion term, mod z less than 1, mod z less than 3, mod z greater than 3 also there. Since mod z less than 1, obviously mod z less than 3 also. So then you can take, that is this function, and split up the terms by partial fractions, and then you can expand the terms by using that binomial expansion, and which gives here what is the terms which having here. I am taking actually it is a z outside, it is a z actually, and then 2z here, and you can take it a 3 outside, it is there. It is the Taylor series contribution, it is a Laurent series contribution. So then that is the first series is valid for mod z less than 1 and second series is mod z less than 3. Since that is the both series are valid within the domain mod z less than 1 there. So then, and the second term that here, it is mod f of z equal to z plus 1, again you can split up as good as this one, and again you take it, that is the z outside using this one, because since we can take it, that is the mod z less than 3 here. So here you can take it a constant, because since it is the greater than that. So that's what I am taking. It is 2 outside, 3 outside there in the second term, and 1 is the z outside there. And you can split up that. You can. It is in the form of it is the Laurent's, and it is the it is the Taylor, because since it is the z term, it is comes in the numerator in every term. So here the first series is valid for 1 over mod z less than 1. It means what? Mod z greater than 2, because since it is the I am seeing that discussing mod z less than 3. So second series is valid for that is mod z less than 3, because each term it is the mod z by 3 less than 1 in that. So that therefore this series is valid between that is the that is mod z lies between 1 and 3. Both the series are valid. And in the third one, it is greater than 3, you can take it, that is the, in both the term, you can take it, that is set outside there, expand that, both are, it is the, in terms of the Laurent series form, and both series are valid, it is the greater than 3 then. So because since the first term, it is the mod 1 over mod z, it means mod z is greater than 1, and mod z is 3 by mod z, it is 3 by mod z, it means what? Mod z is greater than 3. So for mod z is greater than 3, both the series are valid. And next problem we can see that here z square into e power 1 over z about z equal to 0 there. That is different from that one. Just you can see that directly they have asked, that is the Laurent series expansion of the given function z square into e power 1 over z about the point z equal to 0. Z equal to 0, it is the point of z which is lies between that is c and c1 there. That is what. So that now I can take it the function about z equal to 0. Clearly function f of z is analytic at all the points except that z equal to 0 there. So now we can take it z square outside, expansion of e power x, that expansion is, you can x only replaced by 1 over z, that you can have that expansion, and then you can simplify by multiplying z square in each terms, that we got it this way, and 3 factorial terms, that is multiplied with z square, z cube, because since it is what we are having. So this is the required Taylor Laurent series expansion of f of z at z equal to 0 there. And in the problem 6, again we can have an expansion of minus 1 by z minus 1 into z minus 2 in the regions of 3 regions of convergence is given there already, that we can take it a function there and splitting into partial fractions once by using those partial fractions and split up those terms, and then only the points where f of z is not analytic are 1 and 2 there. Only except at that point, so that function is analytic there. Hence function is analytic in mod z less than 1, and hence it can be represented as a Taylor series in a mod z less than 1. So that is why we have expanded form that here. This is what it is, the Taylor series expansion, as we know that, because since it is the terms of every term, it is the in terms of z power something there. That's what. In the second one, that is the one mod z lies between 1 and 2, hence it can be expanded. It is as we know that is it is in the Laurent series there. So that's what you can take it a z outside in both the series. And but thing is that it is the here you can take it 1 and it is that. So that it is the contribution given by Laurent's there. So that is what we have discussed there in that. And in the domain mod z is greater than 2, there you can take it z and z in each term, that both the term, and expand that terms, and then it would be formed this one. And in the seventh problem also we can have the same problems, we can discuss the same thing. So that's what we have discussed.